All right. So once you have Anaconda installed, you can just open this thing called Anaconda prompt. Yeah, unfortunately, I'm using Windows, so I don't really know how to do it for Mac. But if you have Windows, you can follow along. It's probably similar for Mac. So just open Anaconda prompt and then type in Jupyter Notebook. Right. So the Teams, I'm not recording into a public Teams. It's just I'm just recording it, but the recordings are all uploaded on YouTube. So there's a YouTube link that has all the recordings. I'll flash it again at the end of the lecture. Yeah. Right. So we're in like Jupyter Notebook now. And so you just navigate to wherever your file is. If you've downloaded it from, Google Drive, it should be in your downloads folder. But for me, it's in a different folder. Right. So if you see something like this, you've done it correctly. And yeah, this is good. You can follow along. All right. You can start proper now. Shit, I wasn't sharing my screen there. It's okay. All right, great. Can you guys hear me if I just talk like this? Is this okay? All right. Okay. So yeah, thanks for coming, everyone. Welcome to session 2 of the beginner lecture series. So today we'll be building an end-to-end project. So we'll start from like pulling the data from online to processing it, to visualizing it, and also training our model on it, right? So at the end of today, we should get like a fully working model to predict housing prices. Okay, sounds really exciting, right? And there's a lot to cover, so let's get right into it. So this is the second session. There's going to be 2 more sessions in the coming weeks. This is the schedule, right? Yeah. Right. So if you go to this link right here, okay, let me send it again in WhatsApp actually, so that you guys can. Are you in the WhatsApp group? For now, just scan the QR code. But yeah, I'll do the WhatsApp thing. Yeah, if anyone has any issues with assessing the Jupyter Notebook, you can let me know again later. Okay, all good, right? I mean, don't worry too much if you couldn't get it right now. I mean, I'll be showing it on the screen, so yeah. Right, so I just wanted to introduce you to this book. This book's really good. It's really detailed. I'm just like kind of scratching the surface here. And if you want to go more in depth, like this is a pretty good book to do that. It's on O'Reilly, and recently my friend told me like all Imperial students have free access to like books on O'Reilly apparently. So yeah, you can get it for free if you log in with Imperial. Yeah, really good book. Okay, so as I mentioned just now, we're gonna be predicting housing prices today. Okay, so this is what we'll go through. First, we'll do a little introduction to what is ML, and then we'll dive into the code itself and code out the whole project. Right, so a quick recap of lecture 1. I forgot to put something on this slide. But basically, from lecture 1, we were learning about basic Python. And the most important things you need to take away from that lecture is basically how to import modules. Modules are basically Python files, and we'll be importing a lot of modules and using other people's modules today. Yeah. So some tips before we start. Don't worry too much about the code details. Like the purpose here today is to learn about the workflow process, not to get like too much into the syntax and like all that. Make sure you know like what each step like is for in the workflow process. And this is important because the same process can be applied to any machine learning task. With any machine learning task, you're always collecting data, you're always processing data, and you're always like training and evaluating a model after that. So just try to keep this in mind. Don't worry too much about the code because you can always look at documentation or like I've tried pasting code blocks into ChatGPT and asking it to explain it, and it works like pretty well. So yeah. Right, so quick intro to what is machine learning. So this is a little diagram here. You can see like the big circle is AI or artificial intelligence. And a subset of artificial intelligence is basically machine learning. Where data science comes in is basically data science helps us to process the data before we feed it to a machine learning model. And it also helps us to quantify the performance of our machine learning model, like i.e., how well is our model doing? How accurate is it? Right, so some examples of rule-based AI. So I want to make a distinction between rule-based AI and machine learning. So rule-based AI is like the rules are come up by a human, like the human introduces the rules to a computer, and then it's really rigid, so the computer behaves in a predefined manner. For example, if, okay, sorry, just give people a while to settle down. Right, but for example, if I have a traffic light sensor that turns green only when there's a car present, it's sort of like it only knows how to execute two actions, right? If there's no car, just remain red light indefinitely. But if you detect a car there, then you start a timer before you turn green, right? So it's a pretty simple system. So we can probably use like a rule-based approach to tackle this problem. Another example of rule-based approach would be an automated call assistant. You know, when you get on the phone, like customer service, and then they say like, oh, for this service, press 1, for this service, press 2. So obviously, like, there's an automated call message, and it's rule-based, right? When you press 1, it brings you to like another page. So in terms of like code, you can just imagine it as a bunch of if and else statements. Yeah, so that's rule-based. However, for more complex problems where a rule-based approach doesn't really scale that well because imagine if you had a really complex problem, like for example, you want to identify these handwritten digits. Like I take a camera and I want to identify, oh, is this like a 2 or a 5, for example? So this is not so straightforward anymore because like some of the digits are like really badly written. So this could be an example where machine learning can be used to detect patterns in the data. Other applications could include stuff like facial recognition as well as predicting prices. I mean, you can predict a stock price, but today we're just gonna try and predict housing prices. Right. So now that we've made the distinction between artificial intelligence, like rule-based stuff, and machine learning clear, I want to talk about the different kinds of machine learning. So there's a bunch of different kinds. They're split up into three main groups, namely supervised learning, unsupervised learning, and reinforcement learning. But throughout this course, we're just going to focus on supervised learning. And I'll say, like, as a data scientist or machine learning engineer, most of the problems you encounter will be supervised learning problems. So specifically today, with predicting housing prices, that's going to be a regression problem. It's regression because we're predicting a price or like a number. In the case where we were predicting a class, like for example, the handwritten digits, that would be a classification problem instead, because it's like categories. So we're classifying the handwritten digits into 10 different categories from 0 to 9. Right, so I just want to talk a bit about Scikit-Learn. It's basically a library that we'll use. We'll import it and then we can use all of its functionality. It's really good because all of the stuff is just in one place. All the machine algorithms, like Scikit-Learn provides it, all of the model evaluation and selection, as well as integration with other libraries, makes Scikit-Learn a really good package. And here are the other three libraries that we'll see quite often. So we have pandas. We use the pandas data frame. It's just like tabular data, which allows us to manipulate the data easily. We have NumPy, which provides us with NumPy arrays that basically feed into the ML model. And lastly, we have matplotlib, which allows us to plot pretty graphs. All right, great. So these are the main steps when it comes to constructing an ML project. So this is a very important slide. Please try and remember like what's on here, because as we go through the basically building the project, it's good to keep like this in mind so that you don't get lost. But basically for any like machine learning project you undertake, these general steps apply. Yeah, so that's pretty good. Right. So let's look at the big picture. So just to reiterate, today we're going to be predicting housing prices. And before we dive into like the solution, it's good to ask a few questions. So for example, how do you or your organization expect to use and benefit from this model? Right. So this is important. Like it's basically like setting out the goal so that at the end of the project, you can say, oh, I've met this goal, or oh, I did not meet this objective. Right. Secondly, you should think about what the current solution looks like. What's like your baseline level of performance? So in terms of the housing price predictor, maybe the current solution is like literally a human like sitting in front of a computer and trying to predict the housing prices, like a housing expert, you know. So the ML model comes in to basically automate the process and to help the company save costs. Third question, should we use supervised, unsupervised, or reinforcement learning? So for today, we're going to be focusing on supervised learning. What this means is that all the data that we get is labeled. So can give an example for this. Yeah, I'm just going to use this example. So for this data set that we're working on, the label is the price of the house, and the data that we use to predict it is other metrics. For example, the number of rooms or the geographical location of the house, or I mean, if you're looking at London houses, you can think about like, oh, how close is it to a tube station, or how close is it to a grocery store? You know, all these factors have an impact on the price of the house, right? So to reiterate, we're trying to predict the price of the house. And when we train our model, it has like all the correct prices and all the metrics. So it looks at the metrics and then it tries to predict the price. Okay, so is this task classification, regression, or something else? It's a regression task because we're going to be predicting a price or a number. Okay, so let's look at how we can get the data. Okay, so let's look at the code real quick. This front part is just a bit of boilerplate code where we import all the packages that we need. And this is just some code that allows us to save the pictures or the figures that we generate to our desktop. Right. Okay. Yep. So this is what the code looks like for importing the data or the CSV file. Again, don't be too daunted by this code. Just remember what the functionality is. So what we're doing here, all we're doing is we're importing the data set from online and we're reading it into a pandas data frame. Okay, so what is a pandas data frame? So this variable called housing is our pandas data frame. A pandas data frame is basically like an Excel sheet. It's just a format for tabular data. So I can use the head method. Method is basically another word for function, but I can use the head method to look at the top 5 rows of the data set. So the first 5 rows looks like this. Okay, let's just look at it for a little bit together. So you can see we have a bunch of columns. I'm just going to read them out. So we have longitude, latitude. This gives us the geographical location of the house. We have housing median age, total rooms, total bedrooms, population, households, median income, median house value, and ocean proximity. Okay, so at this point, I should mention that for this data set, they're not looking at individual houses, but they're looking at houses within a certain district. So for example, they're trying to predict like the price of a house within a certain area. That's why you have like a population metric, because that tells you the population of the district. Right. There's also some other methods that we can use to kind of give us an insight into what this data frame contains. So there's an info method. Here's what it does. So you can see we have 20,000 entries, which means 20,000 rows. And these are basically the features that I talked about just now. So I want to bring your attention to this D-type column over here. This is telling us what data type is in our data frame. So for the longitude column, it only contains floats. Floats are like floating point numbers, like 3.4 or 6.1, stuff like that. Okay, so you can see all of them are numerical, but then there's one down here which is an object. This basically means that either it's mixed, like there's a mix of numbers and words inside, or in this case, it's just words. Okay, so this ocean proximity column, it contains strings or words. I can show you that. So if you look at ocean proximity over here, it says near bay. Yeah, so that's a string, right? That's why over here it's telling us this column's full of objects. So this is important because later on when we do data pre-processing, we need to treat the numbers and the text separately. Okay, well, you'll find out why later. Okay. Yeah, again, just now I brought your attention to the ocean proximity column, right? So these are the text values that are inside that column. You can see that, yeah, we can generate how many times each like string appears. Okay. Lastly, if we want to look at the numerical attributes, we can also use this describe method. So, I mean, it's pretty self-explanatory. You can see here, it tells you the count. That's how many rows. Stuff like average, standard deviation, minimum, maximum, and these are the 25th, 50th, and 75th percentiles. Right now, you don't have to look into anything too detailed. It's just sort of like a brief overview of what's going on. Okay. And one useful thing that we can do is to plot histograms. Okay, so back to the slides here. Yep. Okay, so these are just a few histograms for our data. Wait, sorry, I want to go back a bit. Right, so just now in the data frame, remember that you saw like 10 columns, basically. So these are the values for the 10 columns again. And it's important to note that the median house value, that's what we're trying to predict here. So that is our label. That is also like, that's also what the machine learning model is going to look at. So it will look at these other 9 metrics. So for example, the machine learning model will take into account the geographical location, the age, total rooms, so on and so forth. And using these 9 metrics, it's going to try and predict the median house value. Okay, right. So here we plot some histograms. There's only 9 histograms, not 10, because we can't plot a histogram for the column with the text, as I mentioned just now. Okay, so some observations. For this median income attribute, it's not really expressed in US dollars. It's scaled and kept at 15 for higher median incomes. But in terms of the scaling, it's around like tens of thousands of US dollars. For the housing median age and median value, they are kept as well. So we can tell that it's kept because we suddenly see this like spike here, right? That means all the values above 500,000 here, they're all like binned into like that last value. So for example, if we had a value that was 600,000, they would just convert it to 500,000 because they want to limit it to a certain range. So that's why we have this spike here. So the housing median value being limited to 500,000 is a concern because this is the value we're trying to predict. So you can imagine when we train our machine learning model, it's only going to learn how to predict up to like 500,000. So in a real world scenario, we'll probably go to the people who collected this data and we'll ask them, oh, do you have the full data where it extends beyond 500,000? Or if they don't have that, then we'll tell them, okay, so for predictions where we try to predict houses that are really expensive, you can't trust the model because it hasn't been trained on any of those examples. Yeah. Also, third point, notice that there's very different scales across each attribute. So for example, you can see in this histogram ranges from 0 to 15, right? But then for the house value histogram, it ranges from 0 to 500,000. So this is also a point of concern because when we train our machine learning model, we kind of want all the columns or attributes to be of the same scale, or else the machine learning model will sort of like place a heavier emphasis on this one because the numbers are really big. Yeah. And also many of the histograms are tail heavy. Tail heavy means they have a very long tail like this. So for example, this is tail heavy, this. See, they have a really long tail and the center like of the histogram is off to the left. Right. So now that we've performed our preliminary like look at the data, it's time to separate the data into a training set and a test set. Okay, so The reason why we separate into a test set is because we want to evaluate our model at the end of the day. So let's just say you're the machine learning like guy at a company. And then after you create a model, your boss asks you, okay, so how's this model gonna like perform in the real world? Let's just say I take like a house that the model has never seen before. Like how are you gonna predict its cost, right, or its value? So in order to get like an accurate representation of how our model is gonna perform in the real world, we section off a part of the data and then we call it our test set. So eventually when we try to see how our model is gonna perform after we train it, we bring in this test set and we basically pretend it's like new data, right? So the reason why we split away the test data so early on is because after this, we're going to start visualizing the data like more in depth. So as a human, you don't want to look at the test set at all because your brain is like really, really quick to pick up unseen patterns in the data. And then if you look at the test set, you might get influenced by it. So the best thing to do is just set it aside and don't ever look at it until you're ready to evaluate your model's performance at the end. Okay. So how exactly should we split up the training data and the test data? Because just now I mentioned there were 20,000 rows, right? So we want to split this 20,000 rows or training examples into a training set and a test set, right? So usually what people do is they just take 80% of the data for the training set and they take 20% for the test set. I mean, this number is pretty arbitrary. Like nothing's stopping you from taking like 30% for your test set, for example. It's just a rule of thumb and it works pretty well. Okay. There's another thing to note. So one more thing is of the 20,000 columns, right? How do we decide what goes into the test data and what goes into the training data? Do I just take like the first 4,000 as my test data, or do I take the last 4,000, or do I shuffle them randomly and take like 4,000 random samples, right? So the way to do this is usually people would recommend like random sampling, but in some cases that's not the best thing to do. So if I bring your attention to this histogram here, it shows you the number of districts against the income like category. So you can see for different like values of income, there's like different number of the population is basically different. So a lot of people fall into like the middle band, like the middle one, but not many people like earn like in the lower band or the upper band, right? So when we split away the test data, we want to make sure that the test data reflects this distribution. Because for example, if we had a set of test data, imagine we took like the last 4,000 entries and that 4,000 entries only contain like rich people, then our test wouldn't really evaluate our model fairly. And our model might perform like either really well or really bad. And it's not really a fair assessment, right? So to assess our model fairly, we're going to want to split it according to this distribution. Okay, so how do we do that? Right, so this is some code to do that. Again, don't be too daunted by it. Just keep in mind like what we're trying to do here. We're trying to split up the data into a training set and a test set. And we want to make sure that it follows that distribution that I showed just now. So there's this function that you can import from Scikit-Learn. It's called train test split. So over here, what you're passing it is you pass it the data frame. So this is our data frame, so the tabular data, which is this big guy over here. We tell it the test size. So 0.2 just means I want to take 20% of the data and put it aside for the test set. This stratify argument here is basically doing what I said. It follows this distribution, right? And then this random state is not very important. It's just that the process is like random because we shuffle the data set around. So by assigning a random state, we make sure that it shuffles it the same time every time so that our results don't change every time we run the code. Yeah. Okay, so here are the results. With stratified sampling, which is basically following the distribution, we get like a very small error. Basically, that means that our test data follows the distribution of the original data set. Whereas if we did like a random shuffle and we just randomly took 4,000 out of it, the error is actually quite high. Like you can see here, 6% error for the first income category, right? So this basically means that in like the people who earn quite little, like in the first income category, in the test set, there's 6.45 too many of them. Yeah, so they are like overrepresented in the test set, which is not really what we want. Okay, so now that we've separated the test set from the training set, we're ready to do some data visualization. Okay, so let me explain why is that so. So the training data set is what you eventually will feed into your model. So when you feed this data into your model, you want to make sure that that data is clean and it's good, right? So before we make sure that it's clean and it's good, we have to do like a bunch of processing. So that's what we're going to do here. Right, this is a map of California. The densely populated areas to look at are San Francisco, Los Angeles, and Sacramento. So if I just plot the density of the houses by geographical location, you can see that over here it's really dense. Here is LA and here's Sacramento, right? Using matplotlib, I can also come up with other plots. So in this plot, the radius of the circle represents population and the color represents price. So you can see like the more expensive houses are in the Bay Area over here. Yeah. So I just wanted to talk about correlation. Usually when we try to visualize the data, we want to plot a correlation matrix. So this is just like an example of what correlation looks like. So you have data that kind of like has a straight line relationship like this, then the correlation is 1. But you have something like that kind of looks like a ball, then the correlation is 0. When something has a very high correlation, like a correlation of 1, that means the values are perfectly correlated and they follow each other exactly. So for example, like I can take the height of a person and the weight of a person, that should be correlated positively, because as your height increases, generally like the person's weight will increase, because you have more like bones and everything. Yeah, these are some examples of data that is not linear, so their correlation is 0. So it's quite important to note that correlation only measures linear dependency, so like straight line type of stuff. If you have something that looks like this, like a circle, I mean, obviously there's a pattern there, but it's not a linear relationship, so the correlation is 0, right? Okay, so just to reiterate why we're doing this, as I said just now, we have 20,000 lines of data, right? So it'll be pretty hard for a human to go through all 20,000 lines and to try and like find some patterns or like some intuition from that. So in order for us to quickly visualize the data, like Scikit-Learn or Matplotlib can help us do that by plotting a bunch of correlation graphs. So first on the left, we calculate the correlation between the median house value and all the other features. And then we take the 3 that are basically the highest, and then we plot this correlation matrix. So if I bring your attention to this over here, seems like this graph looks pretty good, eh? The correlation is 0.69. And what this means is basically the median income over here. It means that the median income is a good predictor for median house value. So as the median income goes up, the median house value should go up as well. Right, like in your head, that makes sense, right? If the people earn more money, they're going to buy more expensive houses. So like intuitively, that makes sense as well, right? So one thing that we can do is actually we can try to combine some of these columns. So every entry here is a column in the data set. So we can try to combine some of these columns to generate like more useful features. I'm going to use the term column and feature like interchangeably, but basically the same thing. So we can generate more features by combining some of the old features together. So originally, some of the old features we had were total number of rooms, number of bedrooms, number of households, and population. But as a machine learning expert, like use your intuition and you might say, oh, it might be useful to calculate the number of rooms per house. Might be useful to calculate the ratio of bedrooms to the total number of rooms. And it might be also useful to calculate the number of people per house, right? And in your head, you can sort of like try to predict how these would relate to the price of the house, right? For example, if I have more rooms in the house is probably going to be more expensive, right? And if I have more people per house, it could also point to like positive correlation between the number of people per house and the price of the house. Okay. Right. So now that we've visualized the data, we're ready to start processing it for our machine learning model. Okay. Okay, wait, before that, think I'll just show you the code that was used to do that. Okay, never mind. I'm just gonna skip it because I don't think it's too important. Yeah, you can look at it on your own next time. Right. So just now what we did was data visualization, and that was for us, the human, right? So as the human, like as I said, it's quite hard to trawl through an entire data set of 20,000 values. So we basically use these visualizations to help us. But now what we're doing is we're going to process the data and scale it properly so that we can feed it to a machine learning model. Okay, so these are the steps that we're going to take. We're going to clean the data. We're going to handle the text and the categorical attributes separately. Then we're going to scale all the features so that they're around the same scale. And then we're going to create an automated way to do all of it at once. Okay. Right. So in your data set, it's very possible that there could be missing values. For example, like for some of the entries, they could be missing like number of rooms in the house just cause like they don't know and then like they just left it empty. So in your data set, it will show up as either a blank value or like not a number, you know? So these are represented by the question marks in this figure. So we have a few ways to handle this. We could get rid of all the rows with invalid values. So that means we take this entire entry, like the entire row, and we just remove it from the data set. So that effectively removes the invalid value. We could also get rid of the entire column, like the entire feature. So let's just say there is one entry that is missing like number of rooms, right? Then we say, okay, we'll get rid of the whole like number of rooms column. Okay, you can tell like that's quite drastic. So normally you employ this if there were really a lot of missing values. Say like 75% of the columns all missing values, then you should just get rid of the entire column, right? But the last method, and also the one that we're going to use, is we're going to replace the invalid value with some acceptable value, right? So usually people either use the median of the column or they use like just 0, right? So for example, over here in this column, this first column here, if this value is missing, what I do is I look at all the other values that are present, and then I take the median of that value and I slot that in here. So I basically solve my problem. I have no more invalid values, right? So here's how you do that in code. Scikit-Learn provides this thing called simple imputer. So in this first line, you just import it. And over here, you're creating a simple imputer object. This is just a name that we choose, right? Over here, I have my data frame. And the reason why it's named like that is because I only choose the numerical features. Remember, I had numerical columns, and then I had one column that was words, right? Obviously, I couldn't find the median of like a column that has words. So we're gonna use like only the numerical features. Okay. And then when you call the fit function, basically it transforms this data frame, which is tabular values, into an array, a NumPy array. Okay, I'll show you what that looks like later. Okay, so the simple imputer object over here is a scikit-learn transformer. So it's a kind of an unfortunate name because like usually when people talk about transformers, they talk about like deep learning and large language models. Okay, this is a different thing, yeah. So just keep that in your mind. The transformer we're talking about here is just a scikit-learn object. All it does is it takes in a pandas data frame, which is tabular data, and it spits out an array for you. An array is like a Python list. And we want this NumPy array because eventually when we train our model is going to be trained on a NumPy array. Our model can take in a whole table and like deal with that. It can only deal with numbers. Okay. Right. The next thing we want to do. So just now I talked about replacing the missing values for a numerical column, right? So columns with numbers only. What do we do with the columns that have text in it? So just now you recall like we had an ocean proximity column, and it basically had text like, oh, near the coast or within 1 mile of the coast, something like that, right? So the reason why we need to transform this column is because our machine learning models can only take in numbers. You can't like give it a word. You can't give like a linear regressor a word and try to tell it like, okay, now plot the line of best fit, because like it can only deal with numbers, right? So our problem here is we basically want to convert text into numbers. Okay. So look on the left here. Imagine I have like these categories, red, blue, and green, and I want to encode these categories into numbers. The first thing you might think of is, oh, that's so simple, just assign like a number to each one, Red's going to be category number 1, blue is going to be category number 2, and then green is going to be category number 3, right? So this is called ordinal encoding. Ordinal because like order, like 1, 2, 3. But that's not the best solution, because when you have ordinal encoding, like inherently there's still like a value to that number, right? So for example, here, if I assign the number 1 to red, the number 2 to blue, and the number 3 to green, the machine learning model is going to think, oh, blue is like similar to red because 2 and 1 are close, but then green is not so similar to red because 3 and 1 are further apart. But like in reality, we want them all to be like sort of equally distant away. We don't want the machine learning model to think like, oh, blue is more similar to red than green is, We don't want it to think that. So what we do is we use this method called one-hot encoding. It's really simple. We just create 3 columns, and these are going to be binary attributes. So basically in the column, it's going to be either a 1 or a 0, right? So if you just look at this column here, we have a column for color red, right? So if it's red, then a 1 is going to show up. If it's not red, then it's going to be 0, right? Simple. Okay, so if we want to represent the other attributes as well, blue and green, we can just have columns for those, and then we put either a 0 or 1 in those columns. So if I just run through this example, in this first row here, we can tell that the color is red. In the second row, the color is blue. In the third row, the color is green. And in the fourth row, the color is blue. Okay. So observe that in every row, there should only be one that appears. The rest of the entries should be 0. Because in this example, we can't have a color that's both like red and green at the same time. It's either red, blue, or green. Okay. Right. So this method is known as one-hot encoding. And this slide basically explains what I just said. One limitation of this method is it does not scale well to a large number of categories. So in the previous example, red, blue, green, that's just 3 categories, right? So we created 3 new columns. However, imagine a case where you had 100 categories, right? Imagine like in Imperial, you have like maybe 20 or 30 causes, and you're trying to represent this using one-hot encoding. That would mean you create like 30 new columns out of nowhere. So that might not be a good thing, because when we have too many columns or too many features, that slows down the training process, and it also degrades performance, meaning that our model is going to be less accurate. So if you ever encounter a case where you have too many categories, like you're trying to put like each cause and Imperial into a different category, you should probably use another method like embeddings. So embeddings is used in NLP, where they basically convert like all the categories into a vector, and the weights for this vector are learned through training. Okay, but that's not important because it's not in the scope of this lecture. For today, we're just going to use one-hot encoding. Right. So we're going to use one-hot encoding for the text attributes. And for our numerical attributes, previously we've replaced all of the missing values, right? But there's still some work to be done. So we want to scale all the numerical features so that they're within the same scale. Just now I mentioned that different numerical attributes in the original data set, they have different scales, right? For example, there was one that ranged from 0 to 15, but there was another one that ranged from 0 to 500,000. Like in real world data, you could also have data that has like negative values, but then some features don't have negative values. So all this inconsistency is not desirable, and machine learning models don't like that. They like all their values to be scaled to the same like range or the same like distribution. So in order to scale all your values to the same range, you can use this thing called min-max scaling. You can see the example over here. For example, if my data contains 1, 2, and 3, you can imagine this as a column. It just has 1, 2, and 3. If I were to use min-max scaling, I just scale it so that all the values are between 0 and 1. However, standardization is a bit more robust. What it does is we subtract the average value, and then we divide by the standard deviation. So more or less, we always get a bell curve, because like the mean is 0 and the standard deviation is 1, right? It's like standardizing it to a normal distribution, right? And you can run through the example here yourself. If you take 1, 2, 3, you subtract away the mean, which is 2. So this becomes -1, 0, and 1. and then you divide by the standard deviation to give you these numbers, right? And if you put this into a calculator, it's going to tell you that the standard deviation is 1. Okay, so for this project, we're going to be using standardization. Yeah, sorry. Yeah, correct. So I'm going to get to that in a second. So his question was, what if your original data doesn't follow a normal distribution already? So standardization only works when your distribution is already like sort of like a normal distribution, correct? So yeah, I'm going to get to that now. So as you can see on the left here, this is not a normal distribution. It's very skewed and it's very tail heavy because it has a long tail, right? So to deal with these tail heavy features, instead of just standardizing them, we can calculate the log of the feature. So we just take every input in that column and we take the logarithm, and we'll end up with something that looks more or less bell curve shaped, which is good, which is what we want. Yeah. Another method to do it, if you don't want to take the log, is you can bucketize the feature. So what does that mean? So you can see the distribution that's skewed right on the left. Basically, what that means is you take different sizes of buckets. So for the top that's like really high here, you probably take like a really small bucket so that you basically flatten everything to be a uniform distribution. Whereas for the more sparse like tail here, you take like, you bucket all of this into a huge bucket. Right, so what you get in the end should look more or less like this, like a uniform distribution. But for this project, we're just going to use this method where we calculate the log of the feature. Right. Okay, the last thing that I wanted to talk about in terms of scaling was multimodal distributions. This is what it looks like. So multimodal, because there's more than one peak. Mode basically refers to a peak. So you can see there's two large peaks here. That is so great. So how do we deal with that? Because taking the log is not good enough, right? So we can use this thing called an RBF. I'm not going to get into like too much details, but basically all the RBF does is as you move away from a chosen point. So let's just say we choose this point here, right? As we move away, then this function is going to output a smaller value, right? And a popular RBF function to use is the Gaussian RBF, because the output value decays exponentially as we move away from our chosen point. So don't worry too much about that. Just look at the graph. So this is my Gaussian RBF. And after I scale the data, it should represent a shape like this, which is what we want. Okay. Right, so before I move on, let's just recap everything that I said so far. I know there was quite a lot to handle. So previously, we were talking about processing the features to feed into a machine learning model. So the first thing we talked about was replacing missing values. So we're going to replace the missing values using the median. Secondly, we're going to use one-hot encoding for the text features, the categorical attributes. And then lastly, we're going to scale the numerical features either using standardization, which is the one where we make the standard deviation 1, or we take the log for the case of the tail-heavy features, or we use an RBF in the case of more tricky distributions that are multimodal. Okay. Right. So okay, there's one more transformation that I included. So remember in the data set we had data on the longitude and the latitude of each house, right? So it's possible that longitude and latitude is not very like useful to the model because it's looking at these two features separately. So for example, like longitude is moving from left to right in this feature, in this figure, right? If the model just goes from left to right, can it really identify some pattern in the data? Not really, right? So I want to find a way to combine these two attributes as well. So I'm going to do that using a method called clustering. Okay. All I'm doing here is I am looking at the districts or the groups of houses that have a similar price and similar geographical location. And if that's the case, I'm going to draw an X. Okay. So for example, over here, I draw an X. That means all the houses in that area, they're of a similar price and they belong to the same cluster. Okay. That's all it is. Right. This is just a recap of what we've done. But Gonna move on. So everything that I just mentioned just now, replacing the missing values, scaling the features, and one-hot encoding, you can combine all of these steps into one big transformation pipeline. Okay, a transformation pipeline is just like it's an object that you can import in Scikit-Learn. So this is the implementation for it. So as you can see over here, this is the function that allows us to calculate the ratio between two attributes and so on. But basically what you need to remember is everything that I just said just now, it can be condensed into one step and done all at once. Yeah, that's all it is. Okay. I think I'll show the code for a bit now. Okay, so just to recall, we have one-hot encoding, and then over here we scale the features and transform them. A lot of this code is more for like demonstration purposes. Like for example, I demonstrated how to get this uniform distribution, but we don't actually use it. The most important code that you should look at is let me just show you. Skip all this. Is this chunk over here, right? So this chunk over here, this code, it basically does everything that I said, all together. So at the end, when we put our pipeline together, all we need to do is to pass in our original like training data set, and then we call the fit transform method on it. Okay, so at the end of it, I get this. What does this mean? So over here, I'm passing in a pandas data frame, which again is the tabular data. And after I pass it through this transformation pipeline, on the other side, I get out a NumPy array, which looks like a list of values. And here I'm printing the dimensions of that list of values. So as you can see, I have 16,000 rows. So that means 16,000 training examples. And I have 24 columns, right? The reason why I have 24 columns is, okay, so previously I only had 9 columns, right? The 9 columns that I showed you. How come I have 24 now? So there were additional columns that were generated through the one-hot encoding, right? I think there were around 5 or 6. And then there were also more columns that we generated by taking the ratio between, the number of bedrooms and number of rooms, and also the population per house, right? So that was all additional columns that we generated, and hopefully it will help to train our model better. Yeah. Right. So up to this point, we've visualized the data to gain some insight. We've processed the data to prepare it for our model. And the only thing left to do is to feed it into our model, train it, and evaluate it, right? The most exciting part. Yeah. Okay, so right. So today we're going to look at two really basic models. The beautiful thing about Scikit-Learn is it comes preloaded with machine learning models as well. So the first model that we're going to look at is linear regression. Really nice and simple. Okay, so for those of you who are not familiar, I think this diagram will basically help you understand. It's just plotting the line of best fit, right? So for example, for two-dimensional data on a 2D plane, and you have a bunch of points, right? You just try to plot a line of best fit through it. How exactly do you do that? So we have this thing called a cost function. And what the cost function measures, it measures the amount of error that is present in the line. Okay, I can explain what that is. So this red line here is the line of best fit, right? If you take like a blue point here, that's off the line, you can tell that there's some error, right? It's not on the line exactly. So we basically take the distance to the line, and that's our error for 1 point. To calculate the total error, all we do is we add up all the errors from all the points, and then we just take the average. Okay, so that's one way to calculate the error. For this simplified diagram on the right, as you can tell, it's just a 2D plane, right? So this would be, for example, if we tried to predict someone's weight using their height. Yeah. So for example, this is like weight. For example, if someone is 30 kilograms, they would be 5 meters tall. Again, not the best example, but this is just for using one variable to predict another variable. That's why you can fit it on a 2D plane. But for our example here, we are trying to use 24 features or 24 columns or variables. to predict one output variable, which is the price, right? So that's a bit more complicated, and I mean, it's a bit hard to visualize, but like if you look over here, that's basically what it is. It's this thing called multi-regression, and yeah, basically it's using like more dimensions just to predict one output variable. Okay, so let me explain a bit like about how exactly your computer does this. I mean, if you just pull up Excel right now, it can literally plot like a line of best fit for you, right? But how exactly does it do this? So I'm gonna explain now. So first, we randomly just draw a line through the data, right? So if you know like the equation of the line is y equals to mx plus c, right? So the output variable or the target here is y, and the independent variable is x, right? And the two parameters that we need to tune is m and b or c. Actually, I can't fucking remember what it is, but either b or c, right? So using m, which is the gradient, you can control the slope of the line, and using b, you can control where the y-intercept is, right? So you can shift the line up and down. So using these two parameters, we can basically shift our line anywhere we want to plot the line of best fit. Okay, but how does a computer do this? So first it chooses a random line. Then after that, it measures the distance from each point to the line. So when we square each distance and add them up, this is called like a residual. After that, we try to rotate the line by a bit, and then using the new line, we measure the residuals again. Okay. Right. And we just keep repeating this process. We keep rotating the line, and we keep summing up the squared residuals. Right. So you can see just now I had this original line. I rotated it a bit, calculated the distance from the points, rotated a bit again, do the same calculation. And eventually I'll be able to plot this graph where I have the sum of squared residuals, and I have like the evolution of like the line basically as I rotated it. So using this method called gradient descent, you can basically do some calculus to try and find the minimum point over here, which should give you the line of best fit. And this point over here is the minimum sum of squared residuals, right? So that should also point you to the minimum error that you can obtain, which would point to your line of best fit. Okay. So just now I mentioned for linear regression, it's just y equals to mx plus c, right? But for multiple regression, you just have multiple x's, right? Just x1, x2, blah, blah, blah. Okay. The method is basically the same, like for calculating the cost function. So just now I mentioned calculating the residuals and calculating the error, right? There's a few different ways to do that. So in this project, we'll be using this thing called RMSE, which stands for root mean squared error. Okay, so there's a few ways to do this. The other way is called mean absolute error, also known as Manhattan distance. It's called Manhattan distance because Manhattan is kind of like a grid. So in order to measure the distance between point A and B, you go like sort of like this in right angles to like find the distance. But for root mean squared error, we just go from point A to point B like that, shortest path. So the reason why we use RMSE is it performs a bit better when the outliers are exponentially rare. So you remember just now when I talked about the bell-shaped distribution for our features, right? That means that the outliers are exponentially rare, because if you want to look at something that's at the 99th percentile, the probability of that point coming up is really rare. So that's why we're choosing RMSE. Okay. Sorry, give me a moment. Right, okay, so now let's look at the code for a bit. Okay, so over here, okay, let's point here, it's easier. We can import this linear regression model straight from Scikit-Learn. So all the calculation I just mentioned just now, you don't have to do any of it by hand, This Scikit-Learn package is just gonna handle all of it for you, from taking in the data, to calculating all the residuals, to doing the gradient descent, to find the line of best fit. It's doing all of that math for you. You don't even have to lift a finger. all you need to do is import the module, declare a variable to like store it in. And then what we do here is we make another pipeline. So this pre-processing pipeline was the pipeline for the original data that I was talking about. So it takes in a pandas data frame, which is a tabular data, and then it outputs our values in nice bell-shaped distributions for the model to train on. And then this model over here is our actual linear regression model. You could pass some hyperparameters in here, but if you don't pass anything in, it just uses some default values, right? And then when you're ready to fit it to the data, you just go linear regressor.fit. This is the name of my linear regressor, and then it calls .fit. We are passing it like the raw data frame here because the pre-processing transformer is part of our pipeline. Okay, don't worry about that too much. Just remember, in this one step, we are scaling and processing all the data into a nice NumPy array, and we are also fitting the line of best fit to it in this one line. Okay. Right, so it takes a while to run, but I've already run it when I was in the library just now. So over here, we can just use it to make some predictions. So as you can see here, we just use .predict, and here we are predicting it on the training set. Okay, so these are just some numbers that it's predicting. So over here in this example, we're predicting the first 5 lines of the data set. So what our model is doing is taking in 24 features, and then it's trying to predict one value, right? And we're doing that for the first 5 rows. Okay, so for the first one, we predicted the price was around 243,000. But over here, in reality, it was 458,000. So that's a bit off, okay? So this was only for five rows of data. But like in the original training set, we had 16,000 rows, right? So we can try to see what the total error is on this whole training set. So after it's tried to train, we try to measure the mean squared error, and this is what we get. Sorry, the root mean squared error. So this number, 70,000. So this means that on average, our error, the root mean squared error, is 68,000. Okay, so that's a bit poor considering our houses are in the range of hundreds of thousands, right? Imagine if the real value of a house was, if I just take an example here, if the real value was 101,000, our linear predictor is 60,000 off. That's quite a huge amount. So that's not great, right? So we're gonna need to try and improve it. Okay. So let's try to use a different model. Now I'm gonna use this thing called a decision tree. I'll explain in a bit what a decision tree does, but for now we're just gonna use it. So as you can see, Scikit-Learn is really easy to use. This code is basically identical to the one previously, but just with a few modifications. You can see I just make a pipeline where I have all my pre-processing and the model. If I just scroll up a bit, you can see that it's exactly the same here. The only thing that I change is literally what model I'm using. So here I'm using a linear regression model, but over here, I'm using a decision tree model. And in the same way, Scikit-Learn comes preloaded with a bunch of models that I'm not showing right now. It comes with random forests, support vector machines, and all sorts of cool stuff that I'm not going to show here, but you can go home and try it on your own. So let's try training our decision tree, right? Just fit it on the training data. And then we can do the same thing. Just run through the whole training data set and see what the error is. And we get an error of 0. Oh shit, it's perfect. How's that possible, So when you see an error of 0, usually that's not a good sign, something's wrong. So in order to better evaluate the data, we can use this thing called cross-validation. So previously what we were doing without cross-validation was we were training the model, so basically finding the line of best fit. And then we run through all 16,000 examples in our training data, and then we see how well it predicts each label. Right, so when we get a training error of 0, it means that we ran through all 16,000 training examples and it got all of them correct. Okay. However, this is not a very good way to evaluate our model. So a better way to do it is using cross-validation. Okay, so what is cross-validation? Okay. So cross-validation is basically where we split up our training data even further into these things called folds. Okay, so I know this is a bit confusing, so let me try my best to explain it. So remember, right at the very start, before we started anything, we split up our training data into training data and test data, right? The reason why we're not bringing in the test data yet is because we still want to tweak our model. We still want to make modifications. Our test data is reserved for the very end. The test data is not supposed to improve our model in any way. The test data is just supposed like for us to see how our model would perform in real life so that we can tell our boss, okay, I expect it to like perform with 75% accuracy, or like I expect the root mean squared error to be around 30,000, right? It's for us to give that assurance to the client or whoever is using the model, right? So that's what the test data is for. But when we're still training our model, when we're still making changes to it, we need a way to basically evaluate it more comprehensively. So all we're doing here is we're taking our training data, so that's 80% of the original data set, and we are further splitting it into like smaller parts, okay? So what's going on here is I'm taking my training data set, so 80% of the total data, and I'm splitting it into 5 parts. So one of the parts is going to be a validation set. So this acts as like a pseudo test set. And then I basically run the model 5 times. I take a different cut to be the validation set each time. And then I measure the error on that set. Okay. Do I have code for that? No, I don't. Right, so let's run the cross validation and let's see how it performs. So Scikit-Learn also gives you a really efficient way to do cross validation. You can just import this function, and then you can calculate the cross validation score. So when we do the cross validation on our decision tree, we see that the average root mean squared error is around 66,000, which is a lot bigger than 0, right? So this is a more accurate representation of what the error is like. Okay, so we can do the same thing for a linear regressor, and we see that on average the error is around 69,000. Right, so 66,000 and 69,000, that's not very good. So we're gonna have to try and improve it. So before that, let me explain a bit like what the decision tree is actually doing and what's going on underneath the hood. So this is what a decision tree looks like in terms of a graphical representation. And decision trees can be used for both classifying as well as regression. So classifying is like classifying data into groups, but that's not what we're doing here. We want to predict a score, which is regression. So as you can see here, for the blue rectangles or nodes, we have like a check or like a way to split the data. So for example, I look at this feature x1. x1 could be, for example, the latitude coordinate, right? So if x1 is less than 20, then I want to split. So everything that is less than 20, it goes into the left branch, and then everything that's more than 20 goes into the right branch. Okay, so the decision tree tries to split up the data into like parts, and then at the very end, at the leaf nodes, you get some sort of prediction. So for example, all the examples that are in this node or leaf node of the decision tree, all of their prices would be 300,000, for example. Okay, so how does the decision tree decide where to split the node? In the case of a regression tree, it just tries like a bunch of different thresholds, and then it sees which ones divides the data the best, right? And it's sort of it's a random process how it chooses these thresholds, but it basically tries a bunch and then it chooses the best at each node, right? So what happened with our decision tree just now, why it gave us a training error of 0, was what it did was it kept splitting like smaller and smaller until it had 16,000 leaves, and it basically had 1 leaf for each example. So that's why it could classify the data perfectly, right? It just had 1 leaf for all of the 16,000 examples. So in order to prevent that, we want to do this thing called regularization. Okay, so if you just look at the diagram here, what our decision tree was doing was, it was doing something like on the right here. If you imagine this to be our training data, it was overfitting it. So overfitting is bad because in our training data, it's not perfect. The training data is not a perfect representation of the real world. There could be some noise or some error or some outlier, So overfitting is bad and we want to avoid it, right? Usually a telltale sign that your model is overfitting is if the training error is very low, like close to 0, but your validation error is very high. So just now we saw that the decision tree had a training error of 0, but a validation error of like 66,000. So we know that it's definitely overfitting. Okay. We want something like the middle diagram here, where it generalizes well to the data. So you see, it doesn't try to overfit it like this. It doesn't try to pass through every point, but it follows the general pattern. And using this curve, we'll be able to make good predictions. So we want our decision tree to sort of like be something like that. Okay, how can we do that? Okay, so one way to regularize the decision tree is to prune it. So just now I mentioned that it basically split until it had 16,000 leaves, right? So what you can do is you just limit the max depth that it can go to. So here I'm choosing a max depth of 5. This is just some arbitrary choices to demonstrate to you. You can also select the minimum number of samples. So for example, below 5 samples, it's not allowed to split into a new leaf because previously like it split until there was 1 sample for each leaf. So here I'm setting the minimum number of samples to 5, minimum number of samples per leaf to 2. Oh, sorry, this is for splitting at a higher part. Right, so now that we've regularized it, our results should be a bit better. So if I run the training, I see that my cross-validation error indeed reduces. So it reduced from 66,000 to 64,000. Not by a lot, but it shows that if we regularize the model, it generalizes better to data that it hasn't seen before. Right. Okay, skip this. Another more powerful method we can use is called an ensemble method. So instead of just using one decision tree, we can use many decision trees, train them on small subsets of the training data, and then make them vote on the final outcome. Okay, here it's not voting, but in the case of regression, we're actually taking the average outcome of like a bunch of trees. So this is called a random forest. And when you take many different trees and train them on random subsets of the data, it's also another way to regularize your model and also to make it more powerful. So running this random forest model, we see that our cross-validation score drops to 47,000, which is a huge improvement, right? Okay. We can further fine-tune our model using this thing called grid search. It's a functionality that's available in Scikit-Learn. You just provide it with some hyperparameters, and then it just runs the test like many, many times. So for example, over here, I have a grid of these 3 numbers for the number of clusters. The clusters was the previous map that I showed you where I drew the black X. And then I have also different features, hyperparameters for the max number of features. So what the grid does is it just runs through all of these hyperparameters, trying each combination, and then it does cross-validation for each one. So at the end, when I get the best parameters, I should get like a better performance. Right over here, I see that the error drops by a bit to 43,000. And finally, I can save my model because these models took a while to train, right? So I can save these models using joblib, and then I can load them again at a future date. Right. Oh, sorry. This is a different thing. Sorry. So after we've trained our model successfully, we can proceed to evaluate it on the test set that we haven't seen before. So as I mentioned just now, the test set is just a way for us to gauge the model's performance in the real world, right? So we see that the test error here is 43,000, which is really close to our training error. So when these two values are close, you can tell that, yeah, my model is not overfitting, like it's generalizing well to data that it hasn't seen before, which is the test set. Okay, great. Yeah, so now I'll just do a quick summary and then we can end. Right, so today, we basically went through the basics of what machine learning is. We did an end-to-end project where we started with visualizing the data, getting some insight, and then we proceeded to pre-process the data in a way that was understandable to our machine learning model. Then we learned about 3 different kinds of machine learning models, namely the linear regressor, the decision tree, and the random forest. We learned how to train them, and we learned how to use cross-validation to evaluate their training performance. Some machine learning concepts that we learned were cost function, basically the root mean squared error. We learned about what overfitting is, which is where your model overfits to the training data and doesn't generalize well to data as unseen before. And lastly, we learned about regularization, which is controlling your model, like limiting its like power basically to help it generalize better to unseen data. Okay, great. Yeah, so that's the end of the presentation. It was a whole mouthful and it took really long and it's really hot for some reason. But yeah, thanks so much for coming and thanks so much for listening. If you have any questions, like feel free to ask me now. Any questions? Yeah. Yeah. Yeah, correct. So you could do like you could do just one, like you split off one. So traditionally that's just called a validation set. And yeah, people use that a lot. But cross validation is it gives you a better representation and it's like automated. So Scikit-Learn helps you do it like really easily. Yeah, so it basically doesn't take any effort at all. Yeah. Wait, where did all my friends go? Is there a committee member here? Hey, where's the pizza? Oh, sorry. Sorry. Hey, wait, just where is it?
I think you all should be bringing it in. It's literally right outside.
Okay, the pizza is right outside, but I think we'll bring it into here. Yeah, so yeah, feel free to stick around and ask any questions you have. Yeah.
That before we process the data, we kind of standardize them and make them like to fit in the long tail of the non-distribution like data set itself is not normal distribution.